It's okay, that's fine.
So I will tell you anyway.
And how long it should be?
Like 45-50 minutes.
45. Okay. Unfortunately, unfortunately, I don't know how I will be timing it. I try. Okay.
Okay, hello everyone. Today's speaker is Eva Karovicova. Eva did her PhD at ISO, followed by a first postdoc at the Max Planck Institute in Heidelberg. And currently she's in her second postdoc as a DFG fellow in Heidelberg in the Institute of Theoretical Astrophysics. Okay, so Eva is going to talk about interferometric observations of evolved stars. So welcome, Eva.
Okay. Good afternoon. Thank you for the introduction. So the work I'm going to present today was mainly done with collaboration with Markus Witkowski, Keiichi Onaka, David Bobolts, Eric Fossa, and Michael Schultz. So the main motivation of the project is to better understand the significant mass loss, which is typical for late evolutionary phases for stars. There are, of course, different ways in which stars can lose their masses, depending on their initial mass. For example, stars with more masses, over 20 or 40 solar masses, explode as supernovas in the end of their life, exploring their material from the central core to the interstellar medium. But today we are going to speak about stars with lower masses, stars with masses between 0.6 to 9 solar masses, so-called asymptotic giant branch stars, AGB stars. Here you can see a plot of luminosity versus temperature, and you can see evolutionary track of stars. And you can see the location of asymptotic giant branch stars. It is a phase when stars evolve after main sequence and before entering the phase of planetary nebula and finishing their lives as white dwarfs. For us, it's very important to understand this evolutionary phase because AGB stars are the major source of stellar dust in the interstellar medium, and they are one of the sources of chemical enrichment in the galaxy. And of many stars, a significant fraction, almost 80% of all stars evolve through AGB phase. So it is very important for us to understand because we have to have proper constraints for the stellar models we are using. Here you can see a sketch of an AGB star, and I'm going to record from some basic phenomena. In the center of AGB stars, there is carbon-oxygen core surrounded by two nuclear burning layers. There is the first nuclear burning layer of helium, where helium is undergoing fusion, forming carbon. Then there is a nuclear burning layer of hydrogen, where hydrogen is undergoing fusion to form helium. Those two nuclear burning layers are surrounded by convective envelope. The photospheric abundance of stars depending on the ratio of carbon and oxygen. So the molecular composition in the atmosphere depends on the more dominant element. So for stars where carbon is more dominant, we call them carbon-rich stars, or oxygen-rich stars. AGB stars are known for their pulsations that demonstrate in variation of brightness. So the stars vary in luminosity over 5 magnitudes. For Mira stars, which are a subset of AGB stars, and we are mainly going to speak about Mira stars today, it's a little bit less, it's 2.4 magnitudes. And the period of the cycle for stars is 40 days up to 2 or 3 years. For Mira stars, it's 80 to 1,000 days. Here you can see typical light curve for an AGB star, so it's a V magnitude versus time. And you can see how the brightness changes over, like it's a quite significant changes. Therefore, also AGB stars are quite popular for amateur astronomers because the brightness changes so much. And you can see the cycle. So the peaks for this particular star, the period of the cycle is a little bit over 1 year, 380 days or something like that. There are complex processes in the stellar atmosphere. There is pulsation, convection, mixing, and also shock waves which are propagating through the atmosphere, lifting the material to the regions where the temperature is lower and the conditions are more suitable for forming molecules and later on dust grains. Due to the third dredge-up, which is basically bringing the material from the inner part of the star to the upper part of the star, the carbon is enhanced in the atmosphere. And it is believed that AGB stars follow MSC sequence, where M stars are the stars where oxygen is more dominant, and basically as during the evolution the carbon is enhanced, the stars are evolving to the carbon-rich stars. So the M-type stars, where the oxygen is more dominant, those stars are forming molecules as H2 or CO and SiO, and for dust type, the grains are alumina or crystalline silicates. For carbon-rich stars, the molecules which are formed are CN, C2, and for dust grains, it's amorphous carbon, and graphite. The S-type stars, it's basically intermediate stage for the stars, and it's basically the transform stage between M and C-type stars. When the dust is created, it is believed that due to the large opacity, basically the dust is driven by the radiation pressure on the dust particles, and the dust is pushed away. And around AGB stars, there is large circumstellar envelopes of the material. The radius of AGB stars are very large. They can reach up to 400 or 600 radii of sun. The speed of stellar winds is between 5 to 30 kilometers per second. And the mass loss rate is up to 10 to minus 4 solar masses per year. For Mira stars, it's a little bit less. It's between 10 to minus 7 to 10 to minus 6 solar masses per year. As it was said already, it is believed that radiation pressure is driving the particles away. This concept is a little bit better understood for carbon-rich stars because there the dust grains are opaque enough that we understand the mechanism a little bit better. For oxygen-rich stars, the situation is more complicated. We still don't know which particles are opaque enough, which would allow the radiation pressure to drive the particles away. And we want to understand the dust condensation sequence for oxygen-rich stars, especially for the oxygen-rich stars. We would like to understand which grains are created at which distances from the center of the star, at which phases when the star is pulsating, or if it depends if it is changing from cycle to cycle, not during the phase, like during the maximum, minimum, or between, or if it is irregular over the phases. And it is, of course, clear that the dust grains are going to be multi-component mixture of grains. But today we are going to be focused on two main species, silicate condensate and aluminum oxide. Here you can see a plot of flux versus wavelength, and you can see that silicate have the main features at 9.7 microns and 18 microns, where the 9.7 microns feature is a little bit more pronounced. For aluminum oxide, the feature is not that significant. It's a broad emission feature. It's 11.5 to 11.8 or 13 microns. And it is believed that aluminum oxide is the first solid condensate in the outflow of HEB stars, and it serves as a seed nuclei for condensations of other elements. So in order to better understand the mass loss process, we observe for HEB stars or for Mira stars, RR Aquili, S Ori, GX Mon, and RCNC. We wanted to understand the pulsation mechanism, so we observe the stars over a long period of time. So each of the stars was observed over several epochs. When I will describe you the epochs a little bit later because it involves a lot of observations. So you have to understand that the stars were observed over long time. So here you can see the light curve. So the arrows are the observations, and each of the arrows includes several observations. So we observed like 100 times the star, and we gathered several observations into one, you can see the arrow. So for example, one of the arrows gathers 10 observations because the observations were, the star was observed that close to each other, that was basically at the same time. And we were treating the observation as observed at the same time. We wanted to understand the dust condensation sequence, so we choose the stars according to study Lawrence, Martins, and Pompea, who studied 31 oxygen-rich stars, and they divided the stars according to this, their dust envelopes into silicate-rich dust shells, aluminum oxide dust shells, and combination of those two. So what we did, we selected one star from each of the groups, and RCNC is their addition from aluminum oxide. And what we want to do, we want to understand the pulsation mechanism, so we want to observe the star over a long period of time. So we want to observe the star photosphere and the dust shells. For this, it seems that it's more suitable ground-based observations because we want to observe the star over a long period of time. There are, of course, some disadvantages for ground-based observations because we are facing the problem that we are affected by the turbulence of and the transmissivity of the atmospheres. There are, of course, observing windows, and you can see here the transmittance versus wavelength. And we have in near infrared, we have between 1.1 to 1.4 J band, 1.5 to 1.8 H band, 2.0 to 2.4 K band, and in mid infrared we have 7 to 5, quite large, to 14.5 N band. In those observing windows we can see. If we decide for ground-based observations, we are limited by the effects of the atmospheres, but not only by that, because we are of course limited also by the size of the primary mirror. And if we want to understand in detail the stars, we want to resolve the star using high angular resolution. But if we think about it, that our telescope nowadays, when it's around maximum 10 meters, and with 10 meters telescope, we can resolve in the mid-infrared to 250 milliarc second, but we have to go to 10 milliarc second or even less. So the current technology in those days does not allow us to go to observe in this resolution. So the cost-effective solution for this is interferometry, which is combining light from 2 or more telescopes. It's a superposition of electromagnetic waves. And by this technology, we can reach very high angular resolution. Here you can see a sketch of an interferometer. So you see telescope B, separated by baseline, we will call it. That's basically, as for normal telescope, would be the size of the aperture, and telescope A. And you can see that we are observing the science source, and you see the wave which is arriving to the telescopes. And to the telescopes, the wave is arriving with a little bit of delay. So what we do, we bring the light from telescope A and from telescope B. And in order to combine the light, because in optical interferometry, in comparison to radio interferometry, which in radio interferometry you can record and combine later, with optical interferometry, it's necessary to combine the light physically and at the same time. So there are introduced some delay lines. So basically, the light is delayed by artificially. So by this concept, we can, enlarging the distance between the telescope, we can reach very high angular resolution, up to a few milliarc seconds. So we decided to use very high angular resolution. For that, we decided to use very large telescope interferometer in Chile at Paranal Observatory. And at Paranal Observatory, there are 2 kinds of telescopes. The large telescope, which is unit telescopes, 8.2 meters. And those telescopes, the distance is the baseline between those telescopes, which can be combined into interferometry, is between 47 to 130 meters. There are those big telescopes. Here, and this picture are located here. You can see 1, 2, 3, and 4. And the light can be combined between these telescopes. There are the smaller telescopes, 80s, which are fully dedicated to interferometry. For the big telescopes, they are, of course, observing, they are used for different science, and for interferometry, there is dedicated only 10% of the time, because, of course, it's extremely expensive. But the small telescopes are fully dedicated to interferometry, and for our purposes, the telescopes are, we are using basically mainly the 80 telescopes. And there is a large number of stations. You can see here how many the small dots, and the small telescopes are also movable. The big telescopes are fixed, the small telescopes are movable, so it's possible to have different configurations, so different length of the baselines and different position angles. The small telescopes are 1.8 meters, and the distances are between 11 meters to up to 200 meters, but I think the 200 meters is not active in these days. At the VLTI, there are 2 interferometric instruments. The first is MIDI instrument, and MIDI operates in N-band between 7 to 14 microns. And in mid-infrared, we are sensitive to dust formation zone and inner circumstellar dust shell and chemical composition of the star. There are some details about the mid-infrared interferometer. The interferometer in the mid-infrared combines light only from 2 telescopes and provides visibility and photometry. It's used both the small telescope, ATs, and UTs, the big telescopes. This is 2 technical details that's really not that important. And also there is other interferometric instrument at the VLTI, AMBER. AMBER operates in near infrared and give us the information about effective temperature, which is very important, center to limb intensity variations, and a diameter of the star. And of course, a variation of the diameter over the pulsation cycle. There are some details about the AMBER instrument. AMBER, in comparison to MIDI, is able to combine light from 3 telescopes, which gives us additional information of a closure phase, because in optical interferometry we are not able to record phase, and this is the only way how we can get information about phase. AMBER operates in a 3 resolution mode: high resolution mode, medium resolution mode, and low resolution mode. Again, it is using both kind of telescope, UTs and ATs. Here you can see small, for you to imagine what we are reaching. Here, AMBER is basically operating in near infrared, as I already described. It gives us the information about stuff close to the stellar photosphere. MIDI is reaching a little bit further, so this is the dust shells. And for those of you who do radio interferometry, you can see this is for the masers. And it's of course, because we have quite difficult and complex processes, because we have pulsating atmosphere, and on top of it is sitting dust shell. For oxygen-rich star, in these days, there are not models which would reconstruct the phenomena from the first principles. But we use the best available modeling approach nowadays for oxygen-rich stars. And we used, for describing the inner part of the star, we used dust-free dynamic model atmospheres, which are basically describing the stellar atmosphere, dust-free stellar atmosphere, which is describing the continuum forming photosphere and also the overlying molecular layers. For the dust shell, which we combined with this model, we used radiative transfer model, Monte Carlo radiative transfer model, and the combination of those 2 models is the best possible approach for modeling oxygen-rich pulsating stars nowadays. Here are some details about modeling. So the series there are 2 series of the models. The models were designed for a typical AGB stars, and there are 2 kinds of series, M and P. For our modeling, we used M series because the stars are more close, the parameters of our stars are closer to the parameters of stars the models were developed for. And you can see in the first column, there are the models we were using. And each of the models is, in the second column, you can see, is describing the phase of the pulsation. And we select the models that we would cover the full pulsation period. We are starting from the middle of the first cycle, finishing in the middle of the second cycle. So we are basically describing the full pulsation period. You can see the luminosities and temperature, which are for typical HEB stars are below 3000 Kelvin. So we have 6 dust shell parameters for optical depth. For 2 dust species we are studying, aluminum oxide and silicates. Aluminum oxide were taken from Koike and Begemann, and silicates from Ostenkopf. 2 for inner boundary radii, 2 for power law index of the density distribution. And then we are also delivering the continuum photospheric diameter of the stars, and we are simulating the projected baseline, which are described a little bit later. So we now started with the modeling to better understand what do we expect, actually. What do we expect to observe? So we would like to understand which variation we are expecting in mid-infrared, which variation of the visibility, which variation of the photometry. We would like to understand which is the optimal projected baseline, so what is the optimum distance between the telescope, what is the optimal resolution for us to understand the dust formation, because this is for us the goal, to understand the dust formation. And we want to know what is the optical depth for the pieces, and yeah, I described the dust formation. And here you can see the models we perform. In the red color, on the top you can see flux versus wavelength. On the bottom plot is visibility amplitude versus wavelength. So for the red, this is a typical flux and visibility of stars with silicate-rich dust shell. So you can see that around in the photometry you see the silicate feature, which is also reflected in the visibility I will describe later. For aluminum oxide, it's the curve in green, where the curve doesn't have any significant feature in the photometry in flux. And so here we see again flux versus wavelength and visibility versus wavelength. And we want to understand how, if we expect dust formation, which kind of variability in the curves and the shapes we would be expecting. So here, please be focused on the thick line of the plots. And the numbers are not that important for you. I just only tell you that here, this is describing a star which has silicate-rich dust shell and showing how it would look like if there is a dust formation. There are two models. One is describing phase close to the maximum of the cycle, and one is describing closer to minimum. And here we see 5 plots. The first one is a photometry. It's flux versus wavelength, and 4-time visibility versus wavelength. And here we see two models which are the same, so close to maximum, but the parameters change according to the fact that there will be dust, there will be creation of dust at certain distances. So we are describing the phase of the maximum, but we see that at one plot the dust is created, and in the other plot the dust is not created. So we want to see what variation we would expect. For the flux, there is only one flux because the change of the baseline does not influence the flux. What is those 4 plots of the visibility are the same according to the parameters of the model. Only what is changing is the projected baseline. Only what is changing is the resolution where we go, to which depth of the star we are observing. And you can see that the first one, sorry, wrong button. The first plot, the top, the projected baseline is 60 meters. Then we go lower, 40 meters, here is 25 and 15. And for this star, which is in this case is for silicate-rich dust shell, Ararquili, the optimum baseline where we would, because for the 60 meters, you can see the resolution is not really showing us the difference between those two models, which is one is describing the creation of dust and one is saying that the dust is not created. And we want to, because we have, of course, we are expecting some errors from the observations. And we would like to see the difference is large enough that it will be larger than our errors, uncertainties.
Here you're considering only 2 telescopes, right?
In these 2 telescopes. Yes.
And do you think if you had more telescopes, then you would, because I mean, on the better resolution, you're not being able to distinguish, no? So here you have the largest baseline.
Mm-hmm.
So you have the highest resolution, but you only have 2 telescopes. If you had more telescopes, do you think?
This is not highest resolution. It is highest resolution, you are correct, but somehow we are over resolving. So we are high, but we are over resolving. We are using even too much. For what you say, more. No, because the dust is over resolved there. And it's true that, of course, always more baselines are better. Of course, different position angle is better. And for HGB stars, I will speak about it later. We do not expect that all stars will be spherically symmetric, so that would be. But if we expect spherical symmetry, then more telescopes would not help us because we would reach the same resolution at all projected baselines. So this information is very useful for us because we know now that for future observations, that it would be good for us to observe the stars using these projected baselines, because we are more likely to, if there is a dust formation, we are more likely to distinguish this creation of dust. So, yeah. Yes, not for 2, but it is possible to do for 4. Yes. Doesn't work now. Neither. We changed the battery so it should work, because the pointer is working, but. Mm-hmm. Yeah? Yeah, okay. Thank you. And so I'm showing you only a few simulations because we, of course, did many. So this is what is the influence of optical depth. And again, we see flux versus wavelength, visibility versus wavelength. And in this case, the models are again the same. The parameters are the same. Only in one case, there is addition of aluminum oxide with low optical depth. But on these plots, we can see that addition of aluminum oxide, which has no significant features. So aluminum oxide with low optical depth does not influence the shape of the curves of flux and even more of the visibility, because you would not be able to distinguish. We would not be able to distinguish with the even with the minimum error bars between those 2 scenarios. Here we were reproducing work of Markus Witkowski, who observed our star as Ori in 2007, and he did see some creation of dust closer to the stars. But he did observe the star only at 4 epochs, so he didn't have the ability to compare that many observations. So we wanted to reproduce this case using just modeling, if we would expect creation more dust closer to the star. So in this case, the star is with aluminum oxide-rich dust shell, and you can see again flux versus wavelength, visibility versus wavelength. And we were comparing, and we were reproducing basically what he did see by observations. And again, as in the previous case, this is just visibilities, in this case, versus wavelength. Only what is changing is the projected baseline. And here you can, there are the projected baseline changing. And the optimum for this star is a projected baseline between 45 to 80 meters. In this case, we are more likely to distinguish dust formation. Here, The upper part is flux versus wavelength, visibility versus wavelength, but this is the upper part is observing phase a bit close to minimum of the cycle, and the lower part is again flux and visibility, but is showing the phase close to maximum of the cycle. And here you can see what is the difference when the fraction between aluminum oxide and silicate changes. And the silicate has, of course, a much stronger influence of the shape and features of the spectra. So when we are lowering the amount of silicates, we immediately see the effect on the shape and features of both flux and visibility. For aluminum oxide, the situation is different. So when we are adding or lowering, the features are not that strong, and so we have to be careful when we say that the stars can be described only with silicate dust shell. We have to keep in mind that small amount of aluminum oxide or aluminum oxide with low optical depth can be present, because we are not, we see it from the modeling that basically small amount we would not distinguish. And now we are going to the observational part. So we observed 4 stars and different cycles, and on the top part you see again the observation, the arrows, and here you can see the UV coverage of the observation. So there are different projected baselines and also different position angles as we were covering the UV space. On the top here you can see flux versus wavelength. Here we have close to 70 observations of the star. All the observations for flux were gathered together, because for flux, flux is not influenced by the projected baseline. Anywhere we observe the star, we get the same flux. So all the observations were possible to gather together. For visibility, the situation is different. We have to be very careful here, because we have different projected baseline. In that moment, we have different resolution, and we are observing the star in the different depth. And in the past, there were observations similar to ours, less observations, and also they were not taken into account the different projected baselines, and they were deriving some conclusions. But this is very important fact that we have to distinguish to which resolution we are using. So we divided our observation into 4 different groups, like with observations with longer projected baselines, 20 meters, 20 to 35, 35 to 50 meters, and more than 50 meters. And you can see how you see the visibility and how with longer baselines we are resolving the object better, because object is resolved and the visibility is reaching 0. I will speak about it later. And what we did, we gathered observations. We were observed at the same projected baseline and same position angle in order to be able to say if we see any variation within the cycle. For example, what we want to understand, if there is some differences when the cycle is changing, if we can say that, for example, dust formation was created, so we would expect some changes. As we see in visible wavelength, as the flux is changing, we want to see how it does look like in mid-infrared. So we compare each curve here. It's we gather several observations, and between them the error bars are it's a little bit difficult to explain. I want you to be more focused on that all the curves are lying on top of each other. There are 3 curves, and basically the standard deviation between the observations are the error bars. And you can see that the curves are lying on top of each other and showing us that we don't see any differences when the phase is changing from half of the cycle. So this is a second cycle and half of the phase. Second cycle in the middle, 61, 74, that we don't see any changes. there is another plot showing the same as the phase is changing within the cycle. We don't see any variation for the visibility. Unfortunately, this is the same for cycle-to-cycle variation. Again, the comparison as in the previous plot, and you can see the error bars are very small, and this is a standard deviation between different observations, and the plots are lying really on top of each other. And this is comparison between observations of at the middle, the minimum phase of different cycles of cycle 1, cycle 2, and cycle 3. And again, we do not see any cycle-to-cycle visibility variation. So we do not see any variation, any dust creation within the cycle as the phase is changing, and also if we keep the same phase over the cycle with the visibility. So we don't see any dust creation. For photometry, the situation is a little bit different because we do see some variation, but we have to also keep in mind that photometry is not really precise for mid-infrared. And so the difference is, and we have some uncertainties, and this needs to be confirmed by additional, more precise observations. Again, for cycle-to-cycle photometry, again, we do see some variation, but we have some large error bars in this case. Sorry. So since we did not see any visibility variation, we did deliver for each of the phase, for each of the star, we deliver the optical depth, the inner boundary radii, the power index of density distribution, and the photospheric radii of the star, of course, the effective temperature as well, and the optical depth of the mid-infrared wavelength, because those optical depths are at 0.55 microns. But since we did not see any visibility variation, since we did not see any dust creation, we delivered general description of the star. So we describe the star generally, and we have for each of the star the optical depth, the inner boundary radii, power index distribution, and photospheric radii. And here you can see how the models are fitting to the observations. The fits are very good. So the first is flux versus wavelength, then on the right side, amplitude versus wavelength, uniform disk diameter, Gaussian. For the uniform disk diameter, basically at each point is delivered the diameter of the star as a uniform disk. The last plot is visibility amplitude versus spatial frequency. And you can see that the plots are, you can see that the fits are very good for the observations. This is the results. We did not see there are 4 stars in 4 columns, the observational epochs, and we did not see any cycle-to-cycle visibility variations. But we have to keep in mind that we have the uncertainties are between 5 to 20%. And also, because the stars, the period of the stars is close to 1 year, and the observability of the star is only certain months, we do not have full coverage of the phase. And it's really difficult to, because as it is the period of the star is closer to 1 year, so even if we observe year by year, we are collecting very slowly, we are shifting very slowly. This we have to keep in mind, that we are not covering the full pulsation cycle. But what we saw, we can say that we did not see any visibility variations. For photometry, as I said, we did, but it's necessary to be, we need some additional observations. So we did deliver, we described the dust shells for each of the stars. We deliver optical depth for each of the stars, for RR Aquila of the silicate, and for SRA aluminum oxide, for GX Mon, the combination of those two, aluminum oxide and silicate. We deliver inner boundary radii and the photospheric diameter, which gives us the effective temperature for the star. We perform simulations, which were very important because this is important for us for future observations, which we already did. and the data will be reduced, and we hopefully will see that, the effect of it. And this is a table of mass loss rates for each of the stars. These mass loss rates were adopted from the literature for each of the stars. And we can see, because it is believed that during the AGB evolution, the mass loss rates increases. So as the stars are moving along the AGB, there should be more mass expelled from the star. So our results corresponds with study of a Little Marigny Little and Blumart, which suggested that, because we see that for the two stars which have aluminum oxide dust shells, have lower mass loss rates in comparison to GX Mons, which has a little bit of silicates, and Aquila, which is described by silicate dust shell itself. And they suggested that stars with lower mass loss rates are aluminum oxide dust shells, and for silicates, when the mass loss rate is higher, when the density of the particles is higher, then the silicates are present. So our study agrees with their studies. Sloan and Price suggested opposite scenario, that first are created stars with silicate-rich dust shells, and afterwards aluminum-rich dust shells. But we do see the opposite. And we are coming to summary. We observed the stars using interferometry, oxygen-rich Mara variables. We observed them over several pulsation cycles. We observed them at many different projected baselines using many different position angles. We investigate the circumstantial dust shell and characteristics of the atmospheres. We did not see any intracycle and cycle-to-cycle visibility variation, so we did not see any reflection of dust creation. But again, we have to keep in mind the uncertainties we had and the phase coverage. For photometry, as I said, we need some additional observations. We did model the data using the best available modeling approach nowadays, and we showed that the models we have chosen are able to describe the shape and the features of the observations very well. They fit very well. We did simulations using those models, and the simulations confirm our observations, because in the simulations we also saw that it's very difficult to distinguish if there is a dust formation. We have to be very careful and which baseline, which resolution we are observing, because it's, we cannot simply say there is no dust formation, but we have to be careful and which resolution we go. And our observation is the first such a large study for oxygen-rich stars, because we were really covering long period of time. The stars were observed over several years, and in very much detail, using the best resolution, the best models. So it is very, like, this is the first time. And sorry. And our results corresponds to studies of Lawrence, Martins, and Pompea of the dust shells, because they, as I said, they described stars, 31 oxygen-rich stars divided into group. And as we selected the stars, we can confirm exactly that our stars can be described as well the same way. Markus Witkowski and his study using MIDI data also, again, he described the data using the same models as we did. And we confirm the parameters he derived, so we got the same results. For Keiichi Onaka, he also did not see any visibility variations. But in that case, I think the observations were much less observation, but again, there was no visibility variation. In this case, Zhao Geisler observed using MIDI data, but in his case, he observed carbon-rich stars. It was also a rather extended study, and he did not see any variation as well. So it seems that either we are not sensitive for the variation in the mid-infrared, or again, we have to be very careful about the resolution, and we have to consider in which way we observe the star, or this variation is not demonstrated in mid-infrared, but is demonstrated only in visible wavelength. We also confirm the study of little Marigny and little and Blue Mart, of the dust condensation sequence for our 4 stars. There's the outlook, and we have further interferometric observations using MIDI and AMBER. And in this case, we would like to study also more different dust species, because we have to keep in mind that we used silicate and aluminum oxide. But maybe there are also different dust species which don't have such a strong feature, and it can be also present in the stars. We have data from AMBER instrument, which has 3 telescopes, for image reconstruction. It's very challenging image reconstruction in using interferometry, because it's necessary to have many projected baseline, many positions, angles, so as many telescopes as possible. And it is demanding for time, and it is expensive. But in the future, it will be possible to do image reconstruction in using interferometry, and it brings very important information. We do have some AMBER observations, deep observations, and we can confirm the photospheric diameters. We do have some simultaneous radio interferometry observations. So as we observed the star in mid-infrared and many different epochs, we coordinated the observation in the radio. So we observed the stars at the same time, and we hopefully will be able to compare if there are some effects, how it is reflected in 2 different wavelengths. Of course, we would like to understand what is the shaping mechanism, because we can see that the planetary nebulae are strongly asymmetric. And we would like to see at which phase, or what is the reason of these asymmetries, because it is known that also AGB stars already show some asymmetries. So we want to understand at which point, what is the starting point. And there are the future facilities for interferometry. There is a MATIS which has 4 telescopes, which will offer imaging, and it will operate in N, L, M, and Q band, and will give us the possibility for image reconstruction and gravity, which will increase the sensitivity. As I said, we would like to compare our observations of oxygen-rich stars with observations of carbon-rich stars. We have in our archive some carbon-rich stars, but also it would be nice to compare it with study of Zauer Geisler, who observed the stars also over a long period of time. And we do have in our archive also long-term observation, again coordinated with radio interferometry of some red supergiants. So that would be the next steps. Okay, thank you.
Thanks very much, Iva. Do we have questions?
Do you have an estimate of the errors in the boundary radius that you quoted
for the visibility? Yeah, 5 to 20%. 5 to 20%? Yeah, yes.
More questions?
Are these 4 stars that you're observing one of the shortest period stars?
Those
because maybe if you choose a shorter period one, then maybe you can see.
Yeah. They're not all, like what I was showing you was a star which was close to 1 year, but one of the stars is close to, it's a longer period of time, like it's over 400 days. So the stars we have actually are, it's a little bit more difficult to collect it over the phases. But it's really, also those observations were taken when, because it's hard to collect so much observation, so it's necessary to apply and again and be successful with the proposals, and it's not such an easy task. So to collect these observations, every half a year you have to succeed. it's not easy, unfortunately. Yeah.
So you wanted to probe dust formation,
Yeah.
right, with your
Mm.
observations,
Yeah.
and you found no variability.
With the
What-
visibility. Yeah.
So what does this tell you about dust formation besides the sequence that you found between the aluminum
But
oxide?
it's already very important what we found, that we can see which, because we did find which kind of dust grains are created there, at which distances. It's very important information already. Basically, we could confirm which dust grains are created and which distance is optical depth. So we actually got a lot. That was just the observations. So I don't know if it is. We could say we expected the variation in the visibility. I would not be surprised if there is some, but clearly there is none.
Okay, thank you.
More questions? Okay, thank you, Eva.